We're talking about critical numbers. We found the first derivative. We set them equal to 0, and that got us what? The first derivative is tangent slope. We set it equal to 0, and what did that get us? Max or mins, because tangent slope being 0 is what type of slope? Horizontal slope. And the only way you can get a horizontal tangent slope is if you have a max or a min or a point of inflection, right? Where you inflect, you get a horizontal too. So when we take our first derivative and we set it equal to 0, we get max, min to points of inflection, right? Okay, there's something called the first derivative test, which we've, oh my gosh. The first derivative test, we've already learned. The first derivative test to me is pretty much self-sufficient. We write it, but like you're like, yeah, we know that. So the first derivative test states, suppose that C is a critical number. Okay, guys. Of a continuous function f. It has to be continuous, because if it's not continuous, you can end up having asymptotes and stuff there. And before you ever start a question, you should always say, oh, this is a polynomial. It is XER. Or, oh, this is a rational. Oh, I have some asymptotes or possible points of discontinuity. Oh, or this is a radical. A radical, whatever's in the radical sign has to be 0 or greater, right? Like you have to think about that, get your domain going in your head first before you actually start doing any questions. So for the first derivative test, suppose that C is a critical number of a continuous function f. Then, if f prime changes, so the first derivative changes from positive to negative at C. Remember how we did a number line? So it's going from positive, here's over here. It's going from positive to negative. What do we get? Maximum. F has a local maximum at C. Vice versa, if f prime changes from negative to positive at C, f has a local what? Negative to positive at C. Has a local what? Local minimum. Someone let us down. Now C, if it changes from negative to negative or positive to positive, we said there could be a point of inflection, but what the first derivative just states is if f changes from negative to negative or positive to positive, there is no local min or max. So it's talking about max and mins. So that's the first derivative test. So we're going to use that first derivative test. I'm going to give you example 1. Given f of x equals 3x4 minus 4x cubed. Minus 12x squared. determine now, what's the domain of this function?
XCR.
Why?
It's radical. No, not radical. Polynomial.
It's a polynomial. It's a degree 4 polynomial. It's a quartic function, right? And they're always XCR. So I'm going to get a number line no matter what that goes from negative infinity to positive infinity, right? Yeah. Okay, I think it ran away. Okay, determine A, intervals of increase, decrease. B, max and min. So try that one out, and then we'll talk about the second derivative test. If you're still working, that's fine. So the critical numbers for the intervals of increase, decrease, or where the max and mins will occur, are the first derivative, f prime of x equals to 0, because f prime of x is a fancy way of saying tangent slope, and we're saying tangent slope equals 0, and tangent slope equals 0 whenever you have maxes and mins, because you get horizontal slopes there, right? I agree. So we're trying to find out the critical numbers where f prime of x equals 0. So first off, we have to find f prime of x. So f prime of x equals 12x cubed minus 12x squared minus 24x. And then I always say, if your terms all have x's, GCS something out, correct? Because if not, your test points for synthetic division would be plus or minus 0. That would be the constant of max. It doesn't make sense. So when your constant is 0, always GCF. We can take out a 12x, and we're left with x squared minus x minus 2. And then that factors, we have 12, we have x, we have x minus 2, x plus 1. And these are all equal to 0. The 12 does nothing. X equals 0, 2, and negative 1. So these are my critical numbers of the first derivative. There would be critical numbers of your second derivative as well, meaning totally different things. Their deal with concavity. So if I want where the intervals increase or decrease, I need to make myself a number line. I know it's a quartic function, degree 4 polynomial, which means it's negative infinity to positive infinity domain, which is what you need to find right away off the hop, right? Remember when we did the radical at the end of the day on Thursday, the end of the class? We actually had to restrict it. It wasn't from negative infinity to infinity. Okay, so we fill in our number line. We have negative 1, 0, 2. Now we need to just plug it in. You could plug it into f prime of x, the original function, or you could plug it into the actual factored function, which is a lot faster. So if I plug in negative 2, I would get, that would be my test point, negative 2, let's say. I'd get 12 times negative 2 times negative 2 minus 2 times 2 plus 1. Negative 2 plus 1, sorry. So I would get positive, negative, negative, negative. What does that result in? A negative. So it's actually faster if you just plug it into the factored form, right? So you can just take signs. If I wanted you to graph the first derivative, you'd actually have to find out what that value is, and 2 and whatever that y would be the actual coordinate, but I didn't ask you to graph it. All right. So then the next one I would have, say I plug in negative 0.5. Now I would have 12, negative 0.5, negative 0.5 minus 2, and then negative 0.5 plus 1. So I get a positive, a negative, a negative, a positive. What's that result in? Positive times negative times positive. Positive. And I have to plug in a 1, let's say. I can plug it in down here if I want to. So I get 12 times 1 times 1 minus 2 times 1 plus 1. So I get a positive, a negative, a positive. What does that result in? Positive times negative times positive. Negative. And say I plug in a 3. I would get 12 times 3 minus 1 times 3 plus 1. So I would get a positive, 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 a positive, which results in a positive. So, for A, it said intervals of increase, decrease. Intervals of increase are the positive slopes. And the positive tangent slopes, remember? Guys, if I drew on this one, if I drew tangent slopes on all the coordinates on here, what would my tangent slopes be here? They would be negative, correct? What about this way? They would be positive tangent slopes. They'd be on this side. What about this way? They'd be negative tangent slopes. What about this one? Positive tangent slopes. So whenever your original is increasing, you get positive tangent slopes, which means positive values at the first derivative. And whenever your graph is decreasing, you get negative tangent slopes. So that's why we look for those and we can know if it's increasing or decreasing. So intervals of increase is not how your graph looks. I just threw up random positive. Intervals of increasing. Yep. Trying to talk you right at the same time. So increasing intervals are from -1 to 0, union, or 2 to infinity. Intervals of decrease are -infinity to -1, or 0 to 2. B asks us for max or mins. So I know that on either side of this C value, remember they talked about the C value, what it does on both sides of it? This one decreases, then increases. So what is it at -1?
Min.
A min at -1, and we got to find that something. We'll do that in a second. What about this critical number here, 0? It's an increase, to a decrease, so it is a maximum. And then this one is a decrease to an increase, so 2 is a min. How do I get what the actual values of these are? Plug it into the original. People are like, I don't know if I should put in the derivative, first derivative, or original. Are the max and mins on the original or on the first derivative? The original, so that's why we plug them into the original. So we have to plug it into what the original was. Minus 4x to 3, then what?
Minus 12x.
Okay. So we're going to go f of -1 equals 3 times -1 to the 4 minus 4 times -1 to the 3 minus 12 times -1 squared plus 5. And what do we get for this one?
0.
You get a 0?
I think so. Probably.
3 plus 4 plus 5.
This would be minus 12, this would be plus 4, that would be plus 3, plus 5, and 12 minus 12. Yep. So then we get f of 0, which is 3 times 0 minus 4, 4 times 0 cubed, minus 12, guys. And you get 5. And then you do f of 2. Less talking, more pay attention.
The answer's right.
Well, you don't know because that's finished it.
It's -27. You watched the great. Oh, let me spoil it. Oh, well, look at that.
Okay, does that make sense?
Yes.
Okay, what if I don't give you a polynomial?
No, dude.
Oh my gosh. So this example 1, this was number 1. Number 2 is going to be mathematical. Where did it go? Okay, x. So f of x equals. Guys, x square root 6 minus x. So, this equation is a multiplication of two functions. It's a multiplication of a linear function and a radical, an x and a root x, right? Whenever we have radicals, we have restricted domains. Now remember, the reason why we do composition of functions, addition, subtraction, multiplication, division, which was the last unit we did, is because we know with addition, subtraction, and multiplication, your domain is where both graphs exist, right? Both functions exist. Everyone paying attention because I'm showing something here. So, we technically have two functions here. Remember, we're not always going to have a calculator to look at it and say, oh, it's this. So this would be technically my one function f, and this would technically be my other function g. We agree?
Yes.
It also is that for doing derivatives, so it's kind of cool. The domain of x, it's a line. It's the line x. So it's 1, 1, 2, 2, 3, 3, 0, 0, negative 1, negative 1, negative 2, negative 2. It's the identity line, right? What's the domain of that equation?
X and the reals.
X and the reals. Okay, this one's a radical. We know that what's under the radical has to be greater than or equal to 0. So I can just add my x over, or if I don't add my x over, I minus the 6 divided by negative 1, this inequality sign will flip, correct, whenever you divide by negative? So 6 is less than or equal to x, or we can rewrite it as x is less than or equal to 6, right? So that's the g function, that was its domain. The f function was xer. Where's the combined domain? Yeah, the restricted. So that's going to be actually our domain, right? When you get two functions up. We do. That's why we learned that lesson. It was for this very moment. That's why it's called pre-calculus 12. Making you ready for calculus. All right. So first off, we have to get critical numbers, but we know when we do our number line is going to have to be less than or equal to 6. So it's going to be 6 to negative infinity. We agree? It's not this negative infinity, positive infinity number line anymore. So we're going to do f prime of x is g, which is 6 minus x to the half, f prime, which is 1, plus f, which is x, and g prime, you drop the half in front. I'll just do g prime here. So we drop the half in front, 6 minus x, guys, to the negative a half times negative 1, which is negative a half, 6 minus x to the negative a half. So I'm going to get times negative a half, 6 minus x to the negative a half. This is where I told you that if you guys can't do that GCFing, your critical numbers, you're in trouble for this unit. I told you you're actually not in trouble, you just can't do it. Right? You can't get a critical number. You can't get a critical number, you can't do increasing, decreasing, you can't do max, mins, you can't do any of the question. So that's why I pushed so much that being able to take out GCFs was so very, very important. So out of this one and this one, I can take out a what?
6 minus 1.
6 minus x to the negative a half. What else could I take out?
Negative a half.
Negative a half or 1/2. It doesn't really matter. I'm just going to take out a half. If you took out negative a half, you'll have the same thing, opposite signs. Doesn't make a difference. So we take out 6 minus x to the half, take out a 6 minus x to the negative a half, and I'm left with 6 minus x times what? Okay, 1 divided by half is 2. So I get a 2 here. And then the negative is still here. The half is gone, so I get plus negative x. And then that's gone, right? So I'm left with 1/2, which means 2 goes in the denominator. 6 minus x to the half down here. And then I get 12 minus 2x. So I don't really need the 1. I get 12 minus 2x minus x. And so on the top, I get 12 minus 3x over 2. What could I take out of the top? 3. Don't all answer at once. 4 minus x. Now, if I was drawing the first derivative, would I have an asymptote? If I was drawing the first derivative graph? Yes, because the first derivative has something in the denominator, correct? So I would have an asymptote on the first derivative graph. But the original, did the original have a denominator? Does the original have asymptotes? No, so critical numbers actually come from everywhere. Here, 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 and here, all the denominators. It's not like the denominator can't equal 0. The denominator can't equal 0 for the first derivative, but what's in the denominator still works for critical numbers. Happens to just be our endpoint, that's okay. So we have 4 minus x equals 0, 4 equals x. The 3 and the 2 do nothing. And then we have 6 minus x to the half equals 0. I don't know what I was doing there. Half equals 0. Squared cancels. And then I get 6 minus x equals 0, 6 equals x, which is my endpoint, right? So it can't be a max or min because it's an endpoint. We agree? So the only thing I have here is a 4. Now what if I get a critical number that's outside my domain? Do I still use it? No. And the only time that happens, it's going to happen tomorrow, is when I give you a function, but I give you a restricted domain. So I'll give you a function that has restricted domain. So maybe I give you this function, and I say, but the domain has to be between 0, has to be less than 0. Well, it would kick out all critical numbers. You'd have no max and mins at all, right? It would completely kick out everything. See, that's when you have a restricted domain, which I didn't give you. Okay, so our critical numbers are just 4, really. I guess, and 6, technically. Oh, hit an eraser by accident. Okay, so I need to plug in less than 4 into this, right? So I'm going to plug in 0. People are like, I could plug in 3. I plugged in 2. I'm like, well, the easiest thing I could plug in is 0 because I'm lazy, so I always pick that. If that's an option at all, I pick 0. Yeah. So I'm going to go 3, and then 4 minus 0 over 2. And then 6 minus 0 to the half, which is the square root of 6. So I'm going to get positive, 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 positive. So what's a positive times a positive? Positive. What's a positive times a positive? What's a positive divided by positive? Still x. So if I want you to actually graph the first derivative, you would have to find out what that value is, correct? And then you plot 0 on that value. If I were graphing the first derivative, I'm not asking you anything about the first derivative. Okay, now you plug in a 5. So I get 3, and then 4 minus 5 over 2, and then 6 minus 5 to the half. I'm struggling with already a half. So 3 is positive, 4 minus 5 is negative, 2 is positive. This is 1 half, 1 to the half, which is the square root of 1, which is positive. So what's a positive times a negative? Negative. What's a positive times a positive? That is not meant to be a 1. So this is a negative, this is a positive. What's a negative divided by positive? Negative. So we have increasing from negative infinity to 4, and then decreasing from 4 to 6. Close bracket. So it's equal to the 6. And then we have increasing to decreasing. So what happens at 4? Maximum. At 4 comma what? What did you get when you plugged it back into the original? 4 root 2?
Yeah.
4 comma 4 root 2?
4 comma 4 root 2. Yeah.
Everyone answers at different times, and then just so, especially with the 4 being the x and then the 4 root 2 being the y.
Oh, maybe.
Okay. We're going to discuss the second derivative test. You will love the second derivative test because, guys, you will love the second derivative test because if I ask if something's a max or a min, I don't ask anything about increasing or decreasing, you can literally just plug your critical number into the second derivative and it'll immediately tell you if it's a max or a min. So if I ask for intervals of increase, decrease, you have to do all the work we just did. But if I just ask if something is a max or a min, you do not. So the second derivative test, I want to write it down properly so it's not out of my mouth. Suppose f double prime is continuous near C, which is the critical number. So it just means that C isn't an asymptote, right? Continuous near C. A, if f prime of C equals 0, F prime of C equals 0. What is that just? It's the max or the min or point of inflection. It's a critical number on the first derivative, correct? It's all those x's we were just finding, right? So this is saying if I take the first derivative critical number, that's what this means. If I take the first derivative critical number, so where it equals 0, right? And f double prime of c is greater than 0. If I plug it into f double prime, that same c, if I just plug it into the second derivative and it's greater than 0, then that is a minimum. Then f has a local minimum at c. And vice versa. F prime of c equals 0, so I take my critical number, and then I plug that same critical number into f double prime, and the answer itself is less than 0, so the answer is negative. Then f has a maximum. Our key thing we have to do always, though, guys, is always look at our original and get our domain of that original first. So we're not looking at extra crap that doesn't actually exist on the graph and assuming that it's x here. So using this, let's see if we can go back to our previous questions using our critical numbers and see if they're max or mins just based off the second derivative test, not increasing to decreasing as a max, decreasing to increasing as a min. We can still do that. For the second derivative test, you actually have to know it because sometimes they're going to give you a table of values, which I'll show you in a second, and you can't use the first derivative for it. So let's look back here. Let's go back to our very first one. We want to know if there's max and mins at our critical numbers. We're going to use the second derivative test. So we're going to have a little caveat here. We're going to do the second derivative test. You cannot fit it in there. You can do it below the second derivative test if you so wish. I'm just putting it here so you can see it. What were our critical numbers? -1, 0, and 2, correct? Is that true? -1, 0, and 2. So I'm going to go f double prime of 0. And I'm going to go f double prime of 2. And then I'm going to go f, oops, I skipped one. Sure. F double prime of -1. I don't like these are out of order. Try that again. So in order to fill it as f double prime, what do I need to get? F double prime, and I have to have f prime to get f double prime. So f double prime of x equals 3 times 12, 36x squared, minus 2 times 12, 24x, minus 24. So that's what we're filling it into, right? We're not looking for the critical numbers of the second derivative at all. We're just taking the critical numbers of the first, plugging it into the second. If my answer is positive, it's a minimum. If my answer is negative, it's a maximum. Do I actually even need to know what the actual numbers are? What the value actually is? No, I just need to know its sign. So, I'm going to fill in -1. So I get 3, it's a 3 and a 6. I don't know why it's 3. 36. -1 squared minus 24 times -1 minus 24. So I'm going to get 36 plus 24 minus 24, which equals positive 36. This is actually more what I care about, just that positive sign. Because if I plug it in the second derivative and I get a positive, what is it? Minimum. What was it? A minimum, isn't it? See it? It's minimum at -1, 0. So because this is positive, bless you. This is the minimum. Because of this. I actually don't care what the number is, right? I only care about the sign. So second derivative test can do a very quick min-max figure out. Okay, if I plug in 0, I'm going to get 36 times 0 squared minus 24 times 0 minus 24. which is 0, 0, minus 24, which is negative 24, which is a negative sign, which means it's a what? Maximum. And it was a maximum. Yeah, it's the opposite of what you think. And then a 2, you get 36 times 2 squared minus 24 times 2 minus 24. 36 times 2 is 72 minus 48 minus 24. That results in a 0.
Two squared.
Oh, thank goodness. I was like, we got problems, Lloyd. It's turning out to be a 0.
What if it is 0?
It's not.
What if it was?
Well, if it was, then it wouldn't be a max or a min. It would just prove that we screwed up previously.
So is that possible?
It could be a point of inflection. So whenever your second derivative actually equals 0, which is what we're going to find out after, that is actually a point of inflection. All right. So we get 144 minus 72, which is 72. Which is positive 72, which is, oh, that's an eraser. Yeah, you can have it. Positive 72. Positive, so it is a min. Make sense? So the second derivative test is really fast for finding out if there's mins and maxes. But if I need increasing and decreasing, can I just skip to second derivative test? No, I have to do the original. All right. So we're going to try one other example, example 2. We're going to work through a whole bunch of things. We're going to use all the things we've learned plus the second derivative. So example 2. Determine A, increasing, decreasing. B, max, min. C, points of inflection. And then I'm going to give you a table of values after and see what you do. In a different one. We're going to skip the point of inflection. We'll talk about that tomorrow. Which is y equals x to the 4 minus 4x cubed. Okay, so we take the first derivative of it, we plug in 0 to get our critical numbers. We get them at 0 and 3. We know that this is a degree 4 function, so we know its domain is from negative infinity to positive infinity. We know we have 0 and 3 as our critical numbers. And then we have to plug back into this, which I bracket a whole bunch of times. So I'm going to plug in negative 1. So I'm going to get 4 times negative 1 squared, and then negative 1 minus 3. So I get a positive, a negative, which gets me a big old negative. Then I'm going to plug in positive 1. So I get 4 times 1 squared, and then 1 minus 3. So I get a positive, and a negative. And then I have to plug in like 4. So I get 4, and 4 squared, and then 4 minus 3, which is positive, which is a positive. So I'm going from decreasing to decreasing. And then here I'm going from decreasing to increasing. So what is this one? Point of inflection. And this is a minimum. And your intervals of decrease are from negative infinity to 0, 0 to 3. And then 3 to infinity is the positive. So your intervals of decrease are from negative infinity to 0, 0 to 3. So at 0, it's not decreasing. And then 3 to infinity is our increase. And then our point of inflection is at 0 and something, we gotta plug it back in, so it's 0, 0.
Wait, is 0?
You have to separate it because it's not.
I think I'm getting it.
And then you plug in the 3, and you get
It's not
something.
Increasing it through.
No.
No, that's where there's a horizontal asymptote at.
Oh, yeah. But isn't
And then we go 3, 3, 4 is 81.
Yeah, you have to use 0. There's a max minimum of 0 to 1.
The negative 27.
Yeah.
Your homework is on the board. I'll write it up here. You can have minimums at negatives and maximums at negatives, right?
So if it's a point of inflection, they're right in one form.
Right. Yep. Okay. Your homework from your textbook is page 309. Numbers 31 to 37 odd. 41, 45. I would suggest you do your homework, because this unit is going to fly, and tomorrow we're adding second derivative and restricted domains. Then we're about actually 70% done the chapter. Yeah.
So we're having our unit test on Good Thursday, what was your saying?
Is it Thursday? No, you're not having it this week. Oh, I got a little excessive with the extend page. I meant